All right, let's fly.
Meanwhile, a race car driver is recovering from a horrible accident at Texas Motor Speedway. Check out this video. Drivers are traveling about 200 miles per hour. Wow. And the Chevy 500, when Kenny Brack's car crashed into another car, he was sent airborne before crashing into a steel guardrail. Pieces of that car scattered across more than a quarter-mile of track. Brack suffered extensive injuries. He's listed in serious but stable condition. He had surgery last night for a broken thigh and ankles. He faces more operations for a broken lower back and a broken sternum. The other driver, amazingly, was not hurt.
It says a lot about the construction of these cars and the kind of medical care they get at the track immediately after that.
Stable condition. He had broken lower back. Driver, amazingly, was not hurt.
It says a lot about the construction of these.
So what about the construction of these cars?
And the kind of medical care they get at the track immediately after that.
Before crashing.
Look at these cars, guys.
Into a steel.
Boom! It's like it's just
guardrail. Pieces of that car scattered across more than a quarter. Kenny Brack's car crashed.
This car just broke apart. This car completely broke apart. It's scattered all over the place.
He was sent airborne.
Why do they make these race cars so fragile? I mean, I would have if this were to happen to me, I would have absolutely hated it. Imagine that you're getting rear-ended at a red light, right? So the car is going to explode completely. You're going to be 100% fine, except some of the pedestrians are going to be dead. It's going to act like a roadside bomb. Do you get it? Roadside bomb. Why do they make these cars so incredibly fragile? The regular commercial cars are crushable in order to increase the impact time, right? So we get that. But why is it that they make these race cars so fragile so that they on impact they completely shatter to pieces? What's the reason for it? All right, so guys, you kind of know the answer, right? So what's the answer to that question? Going once, going twice. All right, so increase the impact time. I'm going to give you 5 points for that one. These guys are not trying to increase the impact time so much. They're trying to take the energy away from the driver. All right, because these guys are going at incredible speeds, and these guys are going like over 100 miles per hour, 200 miles per hour. Increasing the impact time is not that easy at that point, because for you to be able to increase the impact time, obviously you have to let the car crumple. Yeah, by breaking the car, you're kind of increasing the impact time, but just a little. The whole idea is to take the energy away from the driver. Take the energy away from the driver. Now, when somebody says that, what does it mean to you? Because most of you guys would have said that, say, about 10 weeks ago, and that would have been a correct statement. You would have said, hey, 10 weeks ago, they make the cars fragile, so the car break apart in order to take the energy away from the driver, right? And that's exactly what you would have said, and that would have been the correct statement. And I would have asked you, I would have said, so that's correct, but what do you mean by energy? What do you mean by taking the energy away? It's kind of weird. Energy is one of those concepts you have an intuitive understanding for, and your intuitive understanding for energy is actually correct. All right, so in a sense that taking the energy away from the driver kind of means that you're taking the force away from the driver, the amount of force that could do harm, right? So you're trying to reduce the amount of force that can harm the driver in essence. So that's what you're trying to do. The concept of energy is a bit of an abstract one, all right? You can't really get to it directly. It's abstract in a sense that the colors are abstract. I mean, when you see the color red, you recognize it. You know that it's going to be different from blue. When you see blue, you recognize it. You know that it's going to be a different color from green, all right? You do have some kind of a recognition for colors, but when you try to describe these colors to a blind person, you won't be able to. And energy is kind of like that. In fact, it's an abstract concept. It's abstract enough so that Newton was actually dancing around the concept. He did not discover it. The concept was discovered during the 19th century, during the Industrial Revolution. And it's been one of the most powerful concepts in physics as well as in engineering today. Now, these guys not only use this concept, but they end up abusing the hell out of it.
As they leapt off the bridge,
here's how I know.
12 per hour, slamming into the water with terrifying force.
Okay, I'm on the outside, helmet cam. Kenny, myself, boys, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reached about 78 miles an hour.
That's all I needed to hear, guys. This is how I know that they end up abusing the concept a little bit.
Oh, right about here.
78 miles per hour.
78 miles an hour.
The cable is 200 feet in length. They are going to go 78 miles per hour right at that point. All right, so that's how I knew that they were using the concept of conservation of energy.
See the harness?
In fact, they're using the concept of conservation of mechanical energy.
Disconnect from the cable right there. Didn't see just.
That's how they done the computations. And furthermore,
disconnect. My arm goes out. Here we come to the water. Pow!
I can tell you that they're hitting the water at 91 miles per hour right there. Give and take. All right. We've done the calculations before. Obviously, we did the projectile motion. But this is a much, much, much more powerful method of running computations. Much more powerful method. This is known as the conservation of mechanical energy, something that we will get into.
Ton of bricks. So look at this plastic, boy. Going into full velocity right here. Probably reached about 78 miles an hour. Right about here. 78 miles an hour.
All right, so 78 miles per hour. How did they know that they were going to go at 78 miles per hour?
You'll see the harness disconnect.
All right, so they obviously computed that.
From the cable right there. Didn't see just disconnect. My arm goes out. And here we come to the water. Pow!
And 91 miles per hour right now.
Oh, with a ton of bricks. So look at this plastic, 40 feet. Big action now.
All right, let me ask you a different question.
Began according to plan as they leapt off the bridge while tethered to the cable.
Stand up.
All right, so for this one, just use the chat line. I'm just curious about what you guys think.
Agree, double? I'm ready. 1, 2, 3, go.
But as the team was about to reach the end of their first arc, the cable snapped, and 4 men and 1 woman.
All right, so they're hitting the water at 91 miles per hour, right? Now, the cable is 200 feet in length, and then they end up falling additional 70 feet. So distance to the bridge. So distance to the bridge is going to be 270 feet. 270 feet. What if these people decided to jump directly into water, guys? Forget about the pendulum move. Just jump directly into water. Do you think they would have? Do you think they would have been going faster, slower, about the same speed? So these guys are jumping directly into water. Do you think they're going to be moving faster, slower, about the same speed? What do you think? Oh my God! Here's the bridge. Here's the bridge. All right. So what if these people decided to jump directly into water? This is going to be 270 feet drop. And when these people did the pendulum move, all right, so they're doing the pendulum move. So they go down, and then here's the cable, and then the harness snaps, and then they hit water right there. And this is going to be roughly 91 miles per hour. So here, do you think they're going to be moving faster than 91, slower than 91, or at 91 miles per hour? So that's what I want to know. Just put it in the chat line. Put it in the chat. All right, so, okay, so Victor says it's going to be slower. Okay, guys, I want you to remember that here, you guys are following unimpeded. Here, they got the cable, right? All right, with the cable in place, notice that they're hitting the water at 91 miles per hour. What if there's no cable? You're falling under the influence of gravity. All right, so just whatever it is that you guys are thinking, if you're right, you will get that 20 points at the end. So this is unimpeded, this one is impeded, you got the cable. So Edward says that they're going to be falling faster. All right, Edward, just give yourself 5 points. Jordan says it's going to be the same. All right, so it covered everything. One person says slower, one person says faster, the other person says it's going to be the same. All right, we'll investigate. Moving forward. Now, which one is more difficult to left? Right, in the chat line, either left or right. All right, this guy is lifting 600 pounds over 6 feet. This guy is lifting something about 6,000 pounds less than an inch. Which one do you think is more difficult to lift? Lifting 600 pounds over 6 feet, or lifting 6,000 pounds for less than an inch? All right, so okay, so both of you guys give yourselves 5 points. If you're right, you guys will get that 20 points. All right, same. It's the left. It's the left. So we got 2 lefts. Galileo's famous incline experiment. So Galileo is trying to figure out acceleration due to gravity by slowing the motion down, and then he makes the observation that if you were to ignore the surface friction, ignoring the effects of surface friction, the ball is going to go back up to the same height. So if you were to ignore the surface friction, the ball is going to go back up to the same height. Basically, that's what he's saying. So why would the ball keep going back up to the same height if the surface friction is ignored? All right, let's get back to the definitions. Energy is the capacity to do work. So if you have energy, you should be able to do work with it. Energy is going to give you the capacity to do work. And when you do work, you transfer energy. So work is a process of transferring energy. All right, so if you were to combine them into a single definition, it goes like this. The energy is the capacity to do work. And when you do work, you transfer energy. So which means that energy is going to give you the capacity to transfer itself. All right, so that kind of definition, you're thinking, yeah, that kind of makes sense, but I don't get it. I don't get it because it's abstract. Okay, guys, that's not abstract. That's stupid. The reason why you don't get it because you end up coming up with this circular argument. All right, the definition itself does not make sense when you combine those into a single statement. All right, energy is the capacity to do work. And when you do work, you transfer energy. But the question is, what is considered work? Work is something that happens when there's a force causing displacement. All right, notice that there's a force acting on the car, and the car is getting displaced in the direction of the force. So which means that this force is causing displacement. This force is causing motion in essence. All right, so the force causing motion, the applied force causing motion is known as work. And whenever you do work, you transfer energy. So energy is the capacity to do work, which means that it gives you a capacity to apply a force on something and make it move. Right? It gives you that ability to generate a force that can cause action, in essence. All right, the proper unit is J. J stands for joules. In the United States, we use calories, more like kilocalories. All right, 1 United States calorie is known as a dietitian's calorie. It's about 1,000 calories in physics. It is 1,000 calories in physics. So you got the conversion factor right there. All right, so the definition of work. This is known as the work energy theorem. right, so work is something that happens when there's force causing displacement. So notice that this mass gets displaced along the x direction. So force causing displacement. All right, in the books, is force times displacement. R is going to be your displacement. R could be x, y, or z. I mean the same thing. So that's your displacement. So force causing displacement is known as work. So the energy is going to give you the ability to do work, which means that it's going to give you the ability to apply a force on a mass and cause that mass to move or get displaced from one place to another. In this case, W is going to be your work. F is your force. R is going to be your displacement. Work is going to be expressed in terms of joules. Force is newtons. Displacement is meters. All right, so in the United States, we use US calorie, which is 1,000 calories in physics or in sciences, which is going to be the same as 4,186 joules. That's what we got. All right, so work is a process of transferring energy, right? So notice that the energy changes. So E is going to be your energy. In this case, energy is changing. It can increase or it can decrease. So E represents energy. Delta means change, so which means that the energy is going to change.
Welcome to the annual AMT Truck Festival in Quebec, Canada, where thousands come to watch chrome-plated and big rig revving action. But this year, they've also come to witness a hair-raising event performed by 42-year-old professional artist and part-time strongman Bernard Rouleau.
The feat that I am going to attempt today is to pull an automobile weighing 2,500 pounds with my beard. Then, at the same time, I'm going to pick up a wheelbarrow weighing 1,000 pounds, pushing it behind me when I'm pulling the car.
But before this hairy Hercules risks one single whisker, he warms up by pulling a pickup with his ponytail.
The strength I use is not just external physical strength. I use internal strength to project my will on the object I pull. My hair, my beard, I don't do anything special. I just use ordinary shampoo. But I do avoid Delilahs who want to cut my hair.
Bernard can trace his strongman roots back 3 generations.
When I was a young boy, I saw a book about strongmen from around the world. But there were no strongmen from Quebec. And strength runs in my family. My mother had extraordinary strength. So I told her that I would be a strongman from Quebec.
Bernard currently holds 10 world records for pulling objects with his hair. But the tangling task of pulling a car more than 19 feet 5 inches with his beard to set a new world record is by far his most challenging feat to date. Inch by inch, step by step, Bernard pulls closer to a new world record. It's a close shave, but with a distance of 19 feet 6 inches, Bernard beats the old record by a hair.
I love to pull cars with my hair. When kids ask me how I do it, I say it just takes a little strength and conditioning.
So in the end, with another world record under his hat, you could say that for Bernard, it was a very good hair day.
I would be a strongman from Quebec.
Hair. But the 5 inches with his beard to set a new world record is by far his most challenging feat to date. Inch by inch, step by step, Bernard pulls closer.
Professor Keenan, we can hear you.
All right, give yourself 5 points. All right, so is he doing any work on the car? The answer to that question is yes, right? He's satisfying the definition of
world record. Inch by
Is he applying a force on the car?
inch, step by step.
Absolutely he is. Is the car moving because of the force that he's applying?
Bernard.
Yes, it is. So that's the definition of work, which means that he's applying a force on the car, and the car is moving because of that force, under the direction of the force. So the work is being done on the car, which means that it's, in essence, transferring energy to the car.
Pulls closer to a new world record.
So this guy's doing work. Where's he from? This guy's from... That's a trick question.
It's a close shave, but with a distance of 19 feet 6 inches, Bernard beats the old record by a hair.
All right, so this guy's from Quebec, Canada, right? What he's doing is actually fairly crazy. So is this what Canadians do normally? Is that the reason why we got a border? So he's pushing up against the crate. Notice that the crate is not moving, right? So this guy's not doing any work. All right, this force, there's no displacement, no work is being done, no energy is being transferred. This force acting on him is also moving along the direction of the force. He's getting displaced in this direction. So the work is being done on him, which means that energy is getting transferred to. All right, put your answers in the chat. Answers in the chat. All right, I see D, so give yourself 5 points for that one. Actually, D is not the best answer. A is the best answer. All right, so for those of you guys who pick D, give yourself 5 points anyway, so it's not a big deal. He's the best answer. Movement does not need to be in the same direction. It needs to be along the direction of the force, but it doesn't need to be in the same direction as the force is. It could be in the opposite direction, or it could be at an angle. All right, so any sort of movement, if the definition of work is force has to cause motion. All right, so which means that the force has to cause displacement. Is the best answer. Not a single person got it. Try not to miss it on this test. All right, it says D here. The correct answer is still A. I have to just change the key. All right, so for work to exist, the force needs to have a component along the direction of motion. So this multiple choice quiz leads into this discussion. Here's the actual force. Notice that it's coming at an angle. It's got a component along the direction of motion. So here's the component of that motion. All right. Once again, here's the actual force causing displacement, and it's got a component along the direction of motion. All right, so force has to be responsible for motion for it to work. All right, so that's the formula. Notice that this time the force is going to be coming at an angle. Here, the force is in the same direction. So the force and displacement are in the same direction. What if the force is coming at an angle just like that? The displacement is happening in this direction. So the force responsible for this motion is going to be the component of this force. All right, so here's the component of this force along the direction of motion. All right, so the component of this force is going to be adjacent over the hypotenuse. So it's going to be force, cosine of the angle of the force that we're going to be looking at. So that's the parallel component of the force. So it's going to be cosine of the angle of the force is going to be along the direction of R, which is going to be responsible for transferring energy in or out of that system. All right, so let's focus on some background stuff that you're supposed to remember from grammar school, stuff from your alphabet. Positive times positive is going to be positive. Positive times negative is going to be negative. Negative times positive is going to be negative. And negative times negative is going to be positive. Just remember that. All right, direction is to the right positive. Left is going to be positive. Up is positive. Down is going to be negative. Force is to the right positive. Left negative. Up positive. Down is going to be negative. All right, so we got the directions. All right. I'm going to set up 3 cases for you. Motion is to the right in all 3 cases. All right, in the first case, the force is going to be to the right. In the second case, the force is going to be opposing the motion. The third case, the force is going to be perpendicular to motion. All right, guys, this force is along the direction of motion. This is in the opposite direction of motion. This is 90 degrees to motion. All right, so let's take a look at the work done on the object. The force is in the same direction as the motion is. Okay, so this is a positive force, positive displacement. Positive times positive is going to be positive. So the energy is going to be gained. Notice that there's a positive change for energy, which means that energy is going to be gained, which means that the object that you're doing work on, this mass is going to gain energy. That's what it means. And the force and displacement in the same direction. It's considered positive. It's considered positive work, which means that the object gains energy. In this case, the force is going to be opposing motion. So object that you're looking at is the mass. All right, so notice that this is negative force, positive displacement. Negative times positive is going to be negative. So it's going to be negative work. So it's going to have a negative effect on the energy, which means that the energy is going to be lost here. Here the energy is gained by this mass. Here the energy is going to be lost by this mass. All right, so which means that negative change in energy means that there's a reduction in energy. Positive change in energy means there's a gain in energy. So the energy is being reduced, energy is gained. So energy is gained, energy is lost. All right, so when the force is opposing motion, the object is going to lose energy. When the force is in the same direction as the motion is, the object gains energy. In this case, the force is in the opposite direction, it's positive. Motion is on the horizontal direction, on the next direction, it's also going to be positive. You're thinking it's going to be positive work. I'm thinking there's going to be no work. The reason is because this force is not a component along the direction of motion. This force does not contribute to motion. That's what it means. This force has no contribution to motion. Yeah, there's force, but the motion is unrelated to the force itself. So no work is being done, which means that there's not going to be any change in energy. So no energy is being transferred, no change in energy. That's what it means. Examples: lifting something up, work done, is going to be positive because force and displacement are in the same direction. All right, so which means that the cat is being energized, which means that energy is being transferred to the cat. Carrying something forward at a constant speed in a straight line. So the speed has to be constant. The direction has to be constant. So which means that there's no acceleration. So carrying something forward, in this case, no work is being done because the applied force is there just to balance the weight of the cat. All right, so the applied force is there, balances the weight of the cat. It's got no component along the direction of motion. So what that means is no work is being done. No work is being done. No energy is being transferred. All right. Lowering the cat down to work on is going to be negative. Apply force in the opposite direction. displacement is in the down direction. The work is negative, which means that the cat is losing energy. All right, so whenever you lift something up, you're energizing the object, so which means that the energy is transferred to the object by lifting it up. Carrying it at a constant speed in a straight line, no energy is being transferred. And whenever you lower that object, you take the energy away from the object.
Who will become world's strongest man? And this is what all the fuss is about. The Husafel stone weighs 410 pounds.
So he's gonna lift a stone which is 410 pounds.
That's about the size of a small...
So that's positive work. He energized the stone. He done some work on it. Force and displacement, they were in the same direction. So he transfers some of the energy from himself to the stone.
car engine. And Greg Ernst has been looking forward to this event for a long time.
Remember, guys, the work is the same as the amount of energy that is transferred, right?
Legend.
So the energy got transferred to the stone. So he ended up losing some of his energy to the stone in essence. So which means that he got a little bit tired by lifting it up.
Hammers believe that
the next step is crucial. Now he's carrying this 410 pound stone.
This stone comes from a sheep pen.
Imagine that he's moving in a straight line at a constant speed. All right. He's probably moving in a straight line, but not necessarily at a constant speed. Imagine that he is.
Carried around a circular course. The farthest distance it was carried was about 60 meters, not by the shepherd, but by his daughter. Just imagine Jane Perry sitting on your chest.
So how much work is he doing on the stone? By physics definition, he's not doing any work on the stone, which means that he's not transferring any energy to the stone from his body. He's applying a force on the stone in the opposite direction in order to balance the weight of the stone, and that force has no contribution to the motion of the stone. So, which means that no energy is being transferred to the stone, no energy whatsoever.
That's the pressure Greg is feeling at the moment. Difficulty in looking to see where he's going over.
But immediately you notice problems. The problem is this guy's getting tired.
The top, but the grip looks
having a hard time walking.
solid.
Look at the face. He's gasping for air. He's got fish mouth going at this point. He's getting really tired. Now, if he's not doing any work on the stone, why is he getting tired? I mean, clearly this guy is losing energy. Clearly, this guy is losing energy. The question is, how is it possible? This guy's not doing any work. He's not doing any work. According to physics, if you're not doing any work, you shouldn't be losing energy. Why is it that the physics is not working out? Or is it? Okay, guys, this is, once again, one of those scenarios. These are amazing test questions, by the way. All right, this is, I mean, I give you the definition. We do a review. I set it up so you know the answer. But on the test, you have a hard time getting to the answer because this requires a little bit of analysis. Now, this guy is getting tired, and there's a good reason for it. Well, because the weight increased, picking up the stone. That's correct. You're in the right path. So what happened? Now, this guy weighs, or appears to weigh more like it, 410 pounds more than what he was, right? Okay. He's not doing any work on this stone. Physics is 100% accurate, provided that he's moving in a straight line at a constant speed. Let's go with that assumption. Let's assume that this guy is moving in a straight line at a constant speed. Let's not change it. So which means that he's not transferring any energy to the stone. The energy is being transferred. He's doing no work on the stone. Yet this guy clearly is getting tired, which means that clearly he's losing energy. So which means that the negative work is being done on him, guys. The negative work is being done on him. That's what it means. What that means is, given the fact that this guy is moving forward, so that the motion is in the forward direction, there has to be a negative force acting on him, opposing his motion or in the opposite direction of his motion. So that you have to identify that force. All right. So the question is, where's that force coming from? Now you have to go back to what enables you to walk. All right. The only reason why we're able to walk and get around because of friction, right? So you apply a force on the ground in the opposite direction of your motion. In turn, the ground applies the same force back on you. This guy applies a force on the ground through friction. Now, this guy appears to weigh 410 pounds more, which means that the frictional force is going to be that much larger. So he's applying a force on the ground. So that's the force in the opposite direction of his motion. In turn, he's trying, and then he moves in the opposite direction of that. He moves in the opposite direction of that force. So motion is in the forward direction, force is in the backward direction. Negative work is being done on it. All right. So as a result, he's losing energy. All right. One of the best ways to lose weight, obviously, is to move around. Walking is one of the best ways to do it because every time you walk, you end up expending energy, which means that you end up losing energy in essence because you're doing negative work on your body. All right, running is the same way. Running requires that you apply a lot more force on the ground, a lot more frictional force on the ground in the opposite direction of your motion. As a result, you end up losing a lot more energy. Driving is the same way. The car applies a force on the ground through friction in the opposite direction of the motion. So what happens? The gas tank is going to start to go down because you end up losing energy. So that's what it means. So negative work. It's how you lose energy.
He's come all the way from Canada.
That's what this guy is also from Canada.
And I'm sure his strength will not let him down now. He's been lifting rocks since an early age. He's even got a 5-year-old.
Canadians are kind of weird. I mean, they're attracted to these kind of weird stuff. One guy is pulling
boy
a truck using his hair. The other guy is lifting rocks, which are 410 pounds.
who is training, lifting rocks.
It's kind of weird because We got plans to go to Mars within the next 10, 15 years, and these guys are still in stone ages.
Onto barrels. Lifting rocks since an early age. He's even got a 5-year-old boy who is training.
That's the future of Canada, guys.
Lifting rocks onto barrels. Like father, like son.
All right, so these are the byproducts of free healthcare, I suppose.
He's gasping for air. And only a couple of meters to go. Not only might we see a new world record, we could be in the presence of a new legend. He's done it.
It's a proud moment for Canada. All right, so the gravitational force extends all the way out to the moon, right? We discussed that like 1,000 times. So force of gravity extending all the way out to the moon. It's well established. How much energy do you think is transferred to the moon by the force of gravity? What's the amount of energy gets extended all the way out to the moon by the force of gravity? What do you guys think? How much work is being done on the moon? How much energy is being transferred to the moon by the force of gravity? All right, I'm going to give you 20 points. I have to time this. How much work is being done on the moon by the force of gravity? All right, so not a single person. All right, so obviously gravity extends all the way out to the moon. If it didn't, we would not have the moon. So the force of gravity extends all the way out to the moon because of it, the moon accelerates towards the center of the circle, right? So no one questions that the force of gravity extends all the way out to the moon. So how much work is being done on the moon? How much energy is being transferred to the moon by the force of gravity? The answer to that question is none. Because this force, here's the direction of motion, and this force doesn't have a component along the direction of motion. So no work is being done on the moon. No energy is being transferred to the moon. So the force of gravity does not add to the motion of the moon. All right, so pick up the best answer and put it on the chat. It's related to the moon question. All right, so a couple of things. Let's make a transition. So we talked about positive work, negative work, and no work, right? All right, so in the case of the positive work, force and displacement are in the same direction. So we'll utilize this formula that you're looking at, and we'll come up with the same answers. All right, if the force and displacement, if they're in the same direction, the angle is going to be 0. All right, so cosine of 0 is going to be 1. So which means that force times displacement times the cosine of the angle, this is going to be 1. So it's going to give you a positive change in energy. So when force is in the same direction as the displacement is, the energy is going to be gained. That's what it means. If force is pointing in the opposite direction, the angle is going to be 180 degrees. The cosine of 180 degrees here is going to be -1. So this thing is going to be -1 that you're looking at. This thing. So it's going to have a negative effect on the change in that energy, which means that the energy is going to be lost. If the force is 90 degrees, cosine of 90 degrees is going to be 0. So force is not going to have a component on the direction of motion. So which means that there's not going to be any change in energy. All right. So we talked about positive work, negative work, and we talked about no work. Yeah. Next question. Which one is more difficult to lift? 600 pounds over 6 feet, 6,000 pounds less than an inch. Okay, so it's better now. All right, so the work equation from the formula sheet. The force causing displacement on the one direction. So this is the amount of work that people get to do. All right, so this is a simple calculation using a formula. Alexa is going to be lifting something 600 pounds over 6 feet. In reality, it says 2 meters, so I have to go change it to 2 meters. So this is 2 meters. Okay, it's over 6 feet. All right, so plug the numbers in, get the answers in terms of joules, and then do a conversion to calories, United States calories. So the work done by Alexa is 1.22 calories worth of work, and the Anderson's work is 0.07 calories of work. All right, obviously, the guy who's lifting 600 pounds, nearly 600 pounds over 6 feet is going to do more work than the guy who's lifting 6,000 pounds less than an inch. How much more? It's 17.5 times more work than this one is. Okay, so what does that mean? What that means is lifting this thing up 600 pounds over 6 feet is going to be 17.5 times more difficult. This is going to be 17.5 times more difficult than this one is. Hence the reason why this is an Olympic sport and this one is a free sideshow. All right. So the question is why? All right, so that's what we need to focus on. This is 600 pounds. This is 6,000 pounds, give and take. This is 10 times heavier, but look at the distance, guys. This thing is, it's 2 meters. This is a centimeter. All right, this distance is 200 times larger than this one is. It's maybe 10 times heavier, but the distance that this guy is lifting, this weight, which is 10 times lighter, is lifting it over a distance which is 20 times larger, 200 times larger, not 20 times, 200 times larger. So, which means that lifting that 600 pounds is going to be a lot more difficult than 6,000 pounds. All right, so work is a process of transferring energy. So whenever you lift something up, notice that you apply a force on something and then make it move against gravity. So the work is being done against gravity. Every time you lift something up, you're doing work against gravity. All right, that's important that you understand and make the connection that every time you lift something up, the work is done against gravity. All right, gravity pulls things down. You force something to move against gravity, so which means that the work is being done against gravity. By lifting something up, in essence, you're transferring energy to that object. All right, so I'm lifting it up from the ground in this direction, applying a force on it. So this mass gets displaced in the upward direction against gravity. So the amount of work that you do against gravity, what you do is you increase the energy of this object. So the energy gets transferred to this object. The energy transferred to this object is known as potential energy. Potential energy, translated in English, it means the stored energy. So you end up storing energy in an object by lifting it up. You positive work on something by lifting it up. And the amount of work that you do is going to become stored in that object. It's the potential energy. All right, so you got the G, so you're doing work against gravity. Okay, so this is the distance, this is the height, this is the location. All right, the higher up you go, the higher the potential energy of this object is going to be. All right, so potential energy is going to be related to height. So P is going to be your potential energy. Letter Y is going to represent the vertical location, the height, or the displacement. The potential energy is going to be expressed in terms of joules. So mgy is going to be the potential energy. So for a given mass, the potential energy depends on the height, it depends on the location. Right, so which one is going to have more potential energy? The people that this guy is lifting or the weights that this guy is lifting? Which one? All right, let's take a look at the problem. Potential energy, do a comparison. All right, so I'm just going to grab everything from problem number 3. All right, so we'll take a look at the potential energy of the weights that this guy's Alexa is lifting versus the people that Anderson is lifting. All right, it's an underlying assumption. Once again, let's use the assumption here. It's going to become interesting. The applied force is in the upward direction. The weight is in the downward direction. You're lifting something up at a constant speed, which means that there's no acceleration. So the applied force is going to be the same as the weight of an object. So you're just matching the weight of an object whenever you're lifting it up. Slightly unrealistic, but we're trying to come up with an estimate here. All right, so potential energy is going to be mg times height. Mg is the same as the weight of an object, remember. So potential energy is weight times the displaced height, just height of that displacement. All right. And then that's the amount of work that you do in lifting something up. Okay, guys, this is the amount of work that you do in lifting something up. This is the amount of energy which is going to be gained by the objects that you're lifting up. All right, now take a look. This is the applied force. Notice that the applied force is the same as W. W is the same as mg. So when you do a back substitution, you end up getting this formula. All right, so when you do a back substitution, so applied force is that, just substitute in there, so it's going to give you mg. So the amount of work that you do in essence is going to be mg times the displacement, which is the same as the potential energy. So what that means is the amount of work that you do and the amount of energy that you transfer are the same. All right, so in lifting something up, you're doing work on the object that you're lifting, which means that you're transferring the energy from your body to the object that you're lifting. All right, so this is the amount of energy that this guy loses, and the Alexa end up losing in lifting 600 pounds over 6 feet. And this is the amount of energy that Anderson transfers to the objects that he's actually lifting. Okay, so that amount of energy leaves their bodies and gets transferred to the object that they're lifting. That's what it means. So the energy gets transferred. All right, so this brings us to the question of why these guys are so chubby. Take a look at Alexa. This guy is breaking the world record in 1976, and notice that these guys look pudgy. All right, heavy weight lifters, power lifters, most of them are going to look pudgy. When you're looking at this guy, he doesn't look impressive. He doesn't. I mean, he's muscular. There's no question that this guy is muscular, but he's not as big as Arnold Schwarzenegger was in 1976. Arnold Schwarzenegger in 1976, this guy was. He was huge in 1976. He was the Mr. Universe in 1976. I mean, his biceps are probably bigger than this guy's thigh muscles. They're probably about the same height. Again, news for you, Arnold Schwarzenegger probably 50 pounds heavier than this guy was. So the question is, who's actually stronger? I mean, you're looking at that. I mean, he's not even flexing his muscles. This may be his driver's license picture, for God's sake. All right, you're looking at this guy, and then you're thinking, wait a minute, which one is stronger? There's no question that you're thinking Arnold Schwarzenegger is stronger. And despite the fact that, this guy is the world record in 1976. All right, this guy is way stronger than Arnold Schwarzenegger. In fact, this guy can run circles around Arnold Schwarzenegger. Why is that he got nothing to show for? If you're looking at his muscles, they're floppy, guys, floppy. And look at these muscles. These muscles are huge. So here's a question for you. Why is it that this guy's not as muscular as Arnold Schwarzenegger is, and yet he's actually stronger than Arnold Schwarzenegger? On top of that, why is he, I mean, obviously this guy is overweight, chubby. Why is he chubby? Why not be muscular and look the part? You're an Olympic athlete. Take pride in it. Damn it. And don't look like a couch potato. Why not look the part? Right. So how is it that this guy is stronger than this guy is? It's not the size of the muscles. The size of the muscles matter in terms of strength. For example, if I wouldn't go up against a guy who looks like this, he would kill me. Big muscles, he's going to be stronger, but he's no way as strong as this guy is, because this guy has a much higher muscle fiber density. Okay, muscle fiber density, which means that these guys are naturally strong. All right, they have a much higher muscle fiber density, which is going to make him stronger. Now, he can be muscular like Arnold Schwarzenegger is, except when you increase the volume of those muscles, the density, muscle fiber density goes down. So they're not going to be as strong. Okay, so obviously he wants to qualify for heavyweight lifting. That's the level he wants to compete, and he needs to get up to that level, which means that he has to make himself heavier. There are two ways of doing it. Number one, he can make those muscles bigger. Bigger muscles will weigh more. But if you make the muscles bigger, fiber muscle density is going to go down. He's not going to be as strong, or he could just gain weight in the form of fat. All right, and that's what these people do. Okay, so they don't want to sacrifice the muscle fiber density, because that's where they get their strength from. Instead, what they do is, they have to make the weight, so that they have to keep eating. So that's what happens. So that's the reason why these guys look pudgy. It's by design, because they don't have a choice. If this guy were to look like this, he's not going to be as strong. He's not going to be able to lift as much. The bigger the muscles are, the smaller the density, muscle fiber density is going to become. Now, another thing that I want you to notice is something that this guy does when he broke the world record. Expended about 1.22 calories of energy. All right, so which means that he lost 1.22 calories of energy, end up leaving his body, got transferred to the object that is burnt 1.22 calories. Let's speak English here. All right, so breaking the world record cost them 1.22 calories of energy. He burnt 1.22 calories of energy. I imagine this is happening in the middle of Cold War, 1976, and these guys are actually trying to make a statement to the world. The statement is, we're stronger than you guys are. We're better than you guys are. So that's the statement that they were making. The Russians were making. Likewise, the Americans were making the same statement. All right, this is a big statement. It would have been more impressive if this guy just broke the world record, all right, and then he puts it down and lifts it up 100 more times within an hour, time and time again, as if this is nothing. All right, in an hour, if he did 100 lift within an hour, it's the same thing, almost 600 pounds. He would have burnt 122 calories, guys. That would have been a 122 calorie workout. Lifting something to 7, world record lifting. You do it 100 times within an hour. It would have been a 122 calorie workout. Now what's happening? He's feeling hungry, right? So he eats one rich cookie and it's going to be more than 122 calories. That's how you gain weight. Powerlifting, you're not going to lose. You're not going to burn a lot of calories. All right. So this is obviously bodybuilding. These are completely different. All right. Next topic: kinetic energy. Kinetic energy is the energy of motion. Now study this. Take all the time you need. I'll give you guys 1 more minute, 10 more seconds. Time's up. That was fast. All right, this car is speeding up, right? All right, it goes from 20 to 30 meters per second. So this is speeding up. So question, is there work being done on this car? All right, so what that means is there a force acting on this car responsible for the motion? The answer to that question is yes, of course there is a force acting on it. How do we know? Because it's speeding, it's accelerating. What causes the acceleration? A force does. Notice that the force is in the same direction as the motion is. So which means that the positive work is being done on this car, which means that energy is being transferred to the car. And notice that the energy appears in the form of motion. It's known as kinetic energy. So the energy is being transferred to the car. So kinetic energy is the energy of motion. You got this mass, it's moving, which means that it's got kinetic energy. All right, so kinetic energy is going to be related to speed. It's going to be related to the square of the speed. So energy is going to be expressed in terms of joules. All right, so and then when you combine kinetic and potential energies together, it's known as mechanical energy. It's a combination of kinetic and potential energies. All right, the conservation of mechanical energy means the constancy of mechanical energy. Mechanical energy is constant, is known as conserved. All right, and when the mechanical energy is conserved, potential energy is going to get converted to kinetic energy, and kinetic energy gets converted into potential energy. So which means that potential energy goes down, kinetic energy goes up at the same amount, and vice versa. All right, the mechanical energy will become conserved only if there's a conservative force acting on the mass. All right, so a force that conserves mechanical energy is known as a conservative force. And prime example of conservative force, one conservative force that we know is gravity. The other one that we will explore is the restoring force. All right, we haven't looked at it, but we will look at it eventually. So if gravity is the only force acting, the nice thing is the mechanical energy doesn't change. Right, so initial mechanical energy right at this point is going to be the same as the final mechanical energy. So what that means is all that potential energy on impact will become just before impact, it's going to be all kinetic. So the bigger the potential energy is, the larger the kinetic energy will be. All right, so it makes
The team's extremely 90 miles an hour. It's a record-breaking pace. Rocketing through hairpin turns at lightning speeds and soaring down straightaways at 90 miles an hour. It just couldn't move the turns with crushing force.
and then they accelerate. Okay, so how did they know that they were going at 90 miles per hour? Okay, it's radar gun. If they don't have a radar gun, you can get an estimate. Right. Ignoring friction, obviously gravity is the only force acting, right? If gravity is the only force acting, mechanical energy remains constant. Notice it's the same number. Potential energy depends on the height, so this is your starting point. As the potential energy starts to go down, the kinetic energy is going to go up by the same amount. Okay, if the accident were to happen right here, you know what the kinetic energy is, right? If you know the mass, you know the speed. Okay, straightforward.
And nothing pushes the G-forces like
All right, so this is
starting high
the last problem that we did.
and dropping fast. Roller coaster in the world. Japan's Fujiyama is the tallest, fastest, and most expensive roller coaster in the world.
So the first drop.
The first hill is 259.
I don't know if this is the first hill, but let's go with it. It's a 259 feet drop. So from this point to the lowest point in motion, I'm just going to assume it's going to be 200.
Top speed, 81 miles per hour.
And the top speed is 81 miles per hour. Okay, so let's take a way to test our theory. Conservation of mechanical energy. All right, so that's it. The tallest drop is going to be 259 feet. We say that the top speed is going to be 81 miles per hour. So when we do the computations, if our math is correct, if the theory is correct, conservation of mechanical energy is correct, we should get 81 miles per hour or something close to it. That's what it means. All right, so what's the speed at this point? It's going to be 81 miles per hour. All right, I usually take my final height with respect to the lowest point in motion. Okay, you can take zero height to be anything you want. Okay, it doesn't need to be the ground. The ground is going to be located here. I usually take it with respect to the lowest point in motion. And with respect to the lowest point in motion, its height, initial height, which is right here, it's going to be 259 feet. Okay. Okay, I goofed this. Okay, so gravity is the only force acting, so we are ignoring the surface and air friction. So which means that mechanical energy is going to remain constant. Here's your initial mechanical energy. Here's your final mechanical energy. So those two will remain constant. So I made the correction. The initial speed is 0. So mechanical energy remains constant. Mechanical energy, by definition, is the combination of kinetic and potential energies. Initial kinetic and potential energy is the final ones. All right, so kinetic energy is going to be 1/2 mv squared. Potential energy is going to be mg times y. All right, so initial speed, initial height. In essence, we're using this formula right here. So here's our mechanical energy formula. It says it's constant. It's a combination of kinetic and potential energies. All right, so we need to solve this for the final speed. Final speed is located right here. And if you have any zeros, plug in the zeros. So that's simply going to simplify the mathematics. Final height is going to be 0, which means that this term is going to go to 0. Initial speed is 0, so that term is going to go to 0. So, all right, so sum for v, which that mass is going to cancel from both sides. Multiply both sides by 2, then get rid of this square by taking the square root. All right, so not simple enough. Okay, immediately you can draw a conclusion, and the conclusion is, in this case, is commonsensical. You know, higher up the object is falling from, faster it's going to be moving. All right, that's what it means in essence. Also, this is the same as the free fall equation. So at the bottom of the motion, it's going to be going at 85. No, it's going to be 40 meters per second, give and take. It's going to be 89 miles per hour. I promise. We end up being 89. We measure that to be 81. Right, that's 81. We end up being 89. Why the discrepancy, guys? Physics is supposed to be an exact science. If it's an exact science, you're supposed to be getting a number which is very close to 81 miles per hour. We're off by 8 miles per hour. Okay, so the question is why? The reason is because we end up ignoring friction, right? Friction has a tremendous effect on motion. Right? So you got 2 types of friction. One of them is surface friction, and you got air friction. Surface friction is dominant in this case. Right? Ignoring the frictional force, the only force acting is gravity. It gives you 89 to 90 miles per hour. It gives you a really good estimate. So the conservation of mechanical energy is usually used to get a really good estimate. And so you get your estimate, it's going to be like 89 miles per hour. So what do? You subtract about 5 to 10 miles per hour from it. It gives you an even better estimate. Right? So the whole idea is to put you in the ballpark. All right. If you're ignoring surface friction, if you're ignoring any sort of frictional force like air resistance, surface friction, whatever, obviously you do so because you're trying to get an estimate, and this gives you a really, really good estimate. So it works out. You're in the ballpark. Right? Actual number is 81. You end up getting 89, and end up getting 89 because you ignore friction. And then that was a good learning experience because now you know that you can actually come up with really good estimates. Right? Mathematics, one of the things that I'm going to share with you guys, mathematics can never capture reality fully. All right, there's no such thing. It's math can only approximate reality. Okay, this is one of those cases. It's in the ballpark. Conservation of mechanical energy is always going to give you a better estimate than for common sense. So this is usually used for these sort of estimates. Not exact, but close enough. That's what it is. Okay, 7:26. Go take a break, and then we're caught on, so we will continue.
That it was part of him, and by letting him be who he was, I could be who I was.
By November of 1998, Osman was looking forward to slowing down and enjoying his family life. He had been pushing hard for many months. He decided to make a final record-breaking fall from Yosemite's Leaning Tower. Assisted by Miles Dasher, Osman packed over 1,000 pounds of equipment to the top of the tower. It took them 5 days to prepare the specialized rigging that he had designed for the jump. A local filmmaker videotaped Dan's thoughts just days before the leap.
Really, it's about adrenaline and having fun with it and just kind of scaring myself in some sick sort of way.
Dan completed a successful 1,125-foot jump on November 22nd. Miles had a successful jump the next day. It was dusk by the time he hiked back up to join Osman.
When I arrived at top, Dano, he was just racing to rush and get it dialed in, and he's trying to tell me that he wants to jump before it gets dark. And I say, I don't think you're going to be able to do that because we got to do this check. And I'm trying to slow him down, don't worry about it. You're not going to get it in the daytime. It's going to be dark.
Dan was convinced that he could push his system just a little bit further. An additional 75 feet would create a record 1,200-foot self-arrested free fall. In order to do this, he would have to drop into a channel between the wall of the cliff and the pine trees beside it.
My biggest fear in this Leaning Tower jump is hitting these 150-foot high pine trees. The reason being is that I'm pushing this jump so far to the deck that these trees are obstacles. What I need to do is target my flight in between the trees so that I don't hit them, because I'm going to be coming in hot below the tree line.
That kind of scared me, just thinking, wow, you're going into past the treetops. You better make sure you nail your mark.
The light was fading quickly, and Osman needed light so he could direct himself into the narrow drop zone. Osman hurried through his system checks, took his position on the edge of the cliff, pulled out his cell phone and dialed.
So we got a call later on that evening, sunset, dusk, and it's Dan saying, okay, you guys ready? Oh, geez, he's going again, So he says, okay, you got me, Miles? 5, 4, 3, 2. Great exit. Pumped it out there chest high, started slowly rocking over, rolling it over into the delta. So he jumped off, and I could hear the wind build up in the phone at my house here. And I was counting his delay, 5, 6, 7, 8, 9, 10, 11, 12, and the phone cut off. And I was like, whoa. And you see his headlights start to disappear off into the darkness. Next thing you know, I just heard just a brief yell, and a tree, sounded like a tree broke in half.
Miles climbed down from the tower and found Dan lying under some broken tree limbs.
And I checked his pulse. I shook him, and I'm like, Daniel, talk to me. Come on, Daniel. And just nothing. He was definitely not with us. And I gave a little prayer on him.
The rope had shredded, killing Dan on impact.
I know things in life go the way they're meant to be, and Dan's life was so the way it was supposed to be. I'm sad for me. I'm sad for Emma. I'm sad for Dan's family and his friends. But I'm not sad for Dan because he had the life.
Okay, so the question is, did he survive the impact? No. Okay, so your initial thought is no. All right, so let's check to see if the impact was survivable. Okay, so we're going to impact analysis or something like that. If you're an accident investigator, you'll probably do something like this. So it's going to be a pendulum knife. So he's got this cable. That cable is, what is it, 200 feet, 1,500 feet in length? No, it's going to be 1,200 feet in length. Okay, that's it. Okay, so you got the cable. So you will walk to the side just a little bit, maybe about 10, 20 yards, and then you would just jump. So the cable is going to stretch, and then it becomes real tight. At that point, it's going to turn into a pendulum move. All right, so you will just keep going at that point, sideways. So what happened was he ended up misjudging how the trees were, so he ended up hitting the top of a tree. The tree breaks, in essence. All right, so 1,200 feet, that's the initial length of the cable that you're looking at, but it's going to be calculated with respect to lowest point in motion. So the lowest point in motion is going to be here. Okay, once again, I take the lowest point in motion to be 0. The length of the cable is 1,200 feet. Initially, he's not moving, so it's going to be 0. I figure out what the speed is at the time of impact. That's going to be, needs to be expressed in terms of miles per hour. During air friction, gravity is the only force acting. So we did the conversion. Gravity is only for force acting, so which means that mechanical energy will remain constant. Which means that the initial and the final mechanical energies are the same. So that allows us to use this formula, kinetic and potential energies. Summation of the kinetic and potential energies for the initial and final cases will be the same. Once again, you got this pure zeros, so plug in the zeros. Final height is 0, the initial speed is 0. That's up for V. Get rid of the masses, get rid of 2. Get rid of the square by taking the square root of both sides. Okay, so algebra is the same as before. So now plug the numbers in. The distance is fast the speed is. So it gives us a number in terms of meters per second. That's almost 200 miles per hour. So this guy was going at roughly about 200 miles per hour. Okay. It's not the speed that matters, it's the acceleration, right? So which means that we have to do impact analysis. Right, so this guy's coming down, hitting the treetop at roughly about 190 miles per hour. So it's getting like 85 to 86 meters per second. Now I have to make a decision. This 190 miles per hour is way too fast. I know that the tree is going to break, so which means that there's going to be an impact down there. But I cannot give it more than 100th of a second. Okay, this speed is way too fast. It's not going to be 10th of a second. The best that I could do for him is 100th of a second. That's the best case scenario. It's probably going to be even lower than this, but the best that I could do is 100th of a second. That's this an estimated impact time. Because I'm trying to check to see if this guy actually survived the initial impact. That's what I'm trying to figure out. And I'll also make the assumption that he hits a treetop, the tree's going to break it, it'll come to a stop. More than likely, just continue at that point. But what happened was the cable got shredded, obviously. All right, so I'll assume that he goes from 180 to 90 miles per hour to 0 within 100th of a second. So if that's the case, what's G? So the tree is going to break, his bones are going to shatter. So acceleration is going to change in impact, so which means that he will experience jerking motion. His final speed is 0, obviously. The initial speed is this. Impact time is going to be 100th of a second. And then we get a number with the decimal to the left. So that's going to give you about 850 Gs. I guess it's an estimate at this point. If this is true, it's going to be direct upon impact. So which means that this guy didn't suffer any pain. It was absolutely no pain. All right, now let's make it a little bit more realistic. 190 miles per hour, the air friction, it's not reasonable. So it's probably going to be around 160, at most 70 miles per hour. So that's an adjustment. I probably gave him too much of an impact time, but I'm going to keep it as is. So it's going to be around 160 to 70 miles per hour with the air friction. So probably didn't come to a stop. Maybe he just moved up in the forward direction. And again, we know that the cable got shredded. So it's probably not going to be 850 Gs. It's probably going to be around 600 to 700 Gs, guys. That's definitely better upon impact. He didn't survive. He didn't survive the impact. Okay, so that's a good thing. If you're going to die, you certainly don't want to suffer. All right, so there was no pain involved. It's responsible what he did, but at least he didn't suffer any pain.
Stand up.
The group is ready for the jump that will change their lives forever.
On 3. 1, 2, 3, go.
78 miles per hour right here. That's what we're saying. All right, guys, cable is 200 feet in length. That's how they do the calculation. All right, so initial speed is 0. Should be going at 78 miles per hour at that point. All right, so this is the final height. I take that to be 0. The lowest point in motion. Initial height is measured with respect to the final height. So that's going to be 200 feet in length. It's the length of the cable. Ignoring air friction, gravity is no force acting. So I got my conversion to meters. Algebra is the same as before, so I'm just going to grab that. All right, so initial speed is 0, final height is 0. All right, so you end up with this formula. So this height is going to be 200 feet in terms of meters. All right, so it's going to be 60.97. So it gives you about 35 meters per second. That's going to be 78 miles per hour. Okay, so
Fallen jumpers.
78 miles per hour right then. And okay, and then we'll hit the water at 90. They shall hit water at 91 miles per hour. Okay, so how do I know that they're hitting the water at 91 miles per hour? Conservation of mechanical energy. All right, so splash down. All right, once again, the final height is going to be measured with respect to the final point in motion. Initial height is going to be measured with respect to final height. All right, so cable is 200 feet in length. They also dropped additional 70 feet, so it's going to be 270 feet. All right, gravity is the only force acting. Bum, bum, bum. Gravity is the only force acting. All right, so which means that mechanical energy is going to be conserved or constant. So which means that we get to use the same formulas as before, same derivation. Speed is going to depend on the initial height. That's going to give you about 91 miles per hour. All right, so that's how it is done. By using the projectile motion formula, we got the same number. So it's 91 miles per hour. Next question. If these people decided to jump directly into water, a distance of 270 feet, how fast do you think they would be moving if that's the case, if these guys decided to directly jump in the water? All right, so the pendulum move, it's going to give you 91 miles per hour. What if these guys decided to jump directly into water? Do you think they're going to be moving faster, slower, about the same speed? So that was a question that we discussed before. Here, these guys are falling unimpeded, right? Here, there's cable, so the cable is going to induce tension, and then it's going to change the direction of this motion. And they will hit the water at 91 miles per hour. So what would happen if these guys were to jump directly into water from a bridge, which is 270 feet high with respect to the water level? All right, so that's the question that we will investigate.
Blaine says he's trying to convince the city of New York to allow him to jump off the Brooklyn Bridge.
Visually, for me, it would just be so amazing to see somebody falling straight down into that water,
So Blaine wants to jump the Brooklyn Bridge.
knowing the dangers that exist.
That's 135 feet up.
That's 135 feet up, guys. Our distance is 270 feet. For those of you guys who haven't noticed that our distance is twice the distance of Brooklyn Bridge, 135 feet up. So if these 5 people decided to jump directly into that water for a distance of 270 feet, that'd be survivable.
A common suicide route.
Once you get beyond 135 feet,
This guy's a medical doctor.
your chances of survival are very slim.
He says you can't survive that. Not very likely.
No, I won't die.
Blaine says he won't die.
But how do you know?
Good question. How does he know?
I won't.
Because he won't.
I'll make sure of it.
He'll make sure of it. I love his confidence. How do you make sure of it? I mean, so you break your neck, your heart stops, and make sure that your soul still hangs onto that body. Is that what it is?
I'm going to train and practice.
Oh, he's going to train and practice. How do you practice for this?
Just to prepare until the point of where I know that, besides wood.
How do you train for this? Something like this. Jump 10 feet, 20 feet, 30 feet, broken leg, take a break. Go back, keep jumping, right?
Floating by or anything like that, I'll be safe.
And he's going to be fine. 135 feet. He says he can do it.
Once you get beyond 135
And the doctor says,
feet, your chances of survival
so the doctor will say no.
are very slim.
Who's right, who's wrong? All right, if you were a betting person, who would you put your money on? Is it the medical doctor who spent nearly half of his life going to school, or David Blaine, who happens to be a magician, considers himself an illusionist? He doesn't like the term magician. This guy absolutely hates the term magician. He gets offended by it. He says, no, I'm not a magician. I'm an illusionist. That's what he does. This guy is a street magician who thinks he's an illusionist. All right, who do you trust with physics? In this case, a medical doctor or a magician who happens to think that he's an illusionist? What do you guys think? Who would you trust? Yeah, you would think that the medical doctor knows what he's talking about, right? Not David Blaine. Absolutely not. All right, let's take a look. So our distance is going to be 270 feet. These guys are debating whether or not 135 feet is survivable. So if our guys decided to jump 270 feet into the water down below, what would happen? That's what we're looking at. So this is what I'm interested in. All right, so this is going to be 170 feet. So we're looking at this one. All right, whether or not it's going to be survivable. I got news for you guys. In terms of the mathematics, what's going to happen is as soon as you jump, gravity takes over, right? So if gravity takes over, what matters is the initial and the final. What matters is going to be the initial and the final heights is the only thing that matters. All right, so the only thing that's going to matter is the initial and the final heights of this motion. All right, so final speed depends on the initial height. In both cases, you have the same initial height, so which means that in both cases, you're going to hit water at the same speed. These guys end up hitting the water at 91 miles per hour, and they end up experiencing in the worst case scenario. They end up landing on their sides, on their backs, and whatever. All right, and so if they were to jump directly into water, they're still going to hit water at 91 miles per hour. In the worst case scenario, they're going to end up landing on their backs, on their sides. So we're looking at the worst case scenario. All right, so jumping directly into water, when you do the impact analysis, they're still going to hit the water at the same speed. Water is going to give, so I'm going to give them 1/10 of a second impact time. And then they'll come to a stop within that 1/10 of a second. In reality, you would start sinking at that point, but forget that. There's going to be a penetration into water. All right, so it's just an estimate. So final speed is going to be 0. They're hitting the water at the same speed in both scenarios. All right, so move the decimal to the left, so it's going to give you about 41 Gs. 41 Gs for a fraction of a second is survivable. You can survive up to 140, so this is like 100 Gs less than what's considered survivable. The problem is you're over 25 Gs. Over 25 Gs, bones will start to break. So survival with broken bones. So that's what you would expect. All right, so you would expect them to be able to survive.
He still thinks it was a good idea.
Remember this guy? This was a 5-second drop. This was a 5-second drop. The height of the bridge was 410 feet. And this guy lands on his back. This was a 50 G impact. He fractured his back, he survived. So 135 feet is survival. It's very survivable. Not only survival, it's very survivable. Okay, so what I think. In both cases, final speeds are going to be the same. Because if you look at this formula, the speed only depends on the initial height. In both cases, you have the same initial height, right? The only difference is this is going to take a little bit longer. This is going to take a little bit shorter. If you want to do sightseeing, this is the way to go. If you're in a hurry, this is the way to go. Worst case scenario here is survival. It's going to be 40 Gs, landing on your side, on your back. So that's what you end up getting. So you more than likely you will end up breaking bones. The worst case scenario here is the same. All right, so you will have broken bones here. Of course, you can break your neck and die from it, but more than likely you will survive the initial impact. So that's where we were at. All right, so more than likely we'll survive that.
He still thinks it was a good idea.
All right, so this is a 5-second drop. It's 450 feet. This guy gets his body fell out of the water. All right, I don't know if that was intentional, but that's what he did. So that's a 50 G impact. So he's back up. That was the
Stand up. The group is ready.
These guys end up hitting the water.
2, 3, go.
It's a 40 G impact because the body's almost parallel to the water. All right, so they really shortened the impact now.
Okay, get on over there. Get on over there. The boats rush to the fallen jumpers, terrified of what they'll find. The scene is chaos. Lori Martin has a broken neck and has stopped breathing. Glenn Rome also has broken his neck, but that doesn't stop him from administering CPR.
Get out of our boat! Don't do this to me! Come on!
All right, so everyone had broken bones.
The other injuries are also severe. Jeff Sargent has been knocked unconscious, and Steve Trotter has 4 broken ribs and a punctured lung. Only Kenny Bunker has escaped uninjured.
So this is the guy who didn't suffer any injuries. Right, so the jumpers. Okay. So the path of motion doesn't matter. The only thing that matters is the initial height in terms of the final speed. All right, so initial height, they have the same potential energy, and in all 3 cases, they will have the same kinetic energy. And all that mechanical energy before impact is going to turn into kinetic energy. So which ball is going to be moving the fastest? In all 3 cases, the balls will move at the same speed. So the path of motion doesn't matter. All objects projected from the initial height with identical speeds will hit the ground at the same